So just giving you a quick recap of what we covered in the last class, right? Last class we were discussing about linear delay model, and the linear delay model says that delay you can define as GH plus P, where GH is also G into H, also known as effort delay F, right? So this is also known as effort delay. This component is parasitic delay. G stands for logical effort, and H stands for electrical effort.
Electrical effect.
I also told you the unit of this one is tau. The unit of this delay is tau, which is supposed to be technology dependent. For example, if I say TSMC 180 nanometer technology, let's say, you may say, let's say the delay is 1 nanosecond. And if you're going down, let's say in 45 nanometer technology, maybe it has been rounded up by 0.1 nanosecond or in picosecond. So it was dependent upon the technology node and the process, right? So the delay is dependent here. Usually this information is given to you, and you are supposed to tell the delay in terms of D or in terms of FO4 delay. I will be telling you, or how to define the delay in that way. I will be telling you. So in this context, so far we have discussed one parameter, which was logical effort. Why do I call this particular model as a linear delay model? You can see this relationship of delay is nothing but a kind of y equal to mx plus c, right? H is a constant. It happens to be constant. It is a ratio of output capacitance to input capacitance multiplied by the logical effort plus p. So it is mx plus c kind of relationship. That is why this model is also known as linear delay model. Now I told you the logic that in order to estimate the logical effort, what you need to do, you need to compare the input capacitance of a particular logic gate with respect to input capacitance of a standard inverter, right? Yes or no?
Yes, sir.
Yes.
Right. Provided that this input inverter and this input or this logic gate has same current driving capability, provided that current driving capabilities are same. Understood? Understood?
Yes, sir.
I gave you a couple of examples. I told you, for example, if you want to design a standard inverter, if let's say mu1 raised to mu p is 2 raised to 1, then you define your standard inverter like this. Look, mu1 raised to mu p basically tells you your holes are the carrier for the PMOS. So PMOS is effectively 2 times slower compared to NMOS. So in order to have the same R values in pull up path as well as pull down path, you need to make sure that NMOS, if NMOS is having a W by L equal to 1, then PMOS should have a W by L equal to 2, right?
Yes, sir.
Yes, sir.
This is the VDD, and I told you from method of RC delay model, you understand that net capacitance which is appearing here is basically 3 times of C for this inverter. And if you want to find out the logical effort of, let's say, 2 input NOR gate, then what you need to do, first you make the topology of 2 input NOR gate, which is very easy to understand. How to make a 2 input NOR gate. NMOS will be in parallel or series?
Parallel.
Right? And PMOSes will be in series. So let's say this is the input A, this is input B, then this is the VDD, this is the ground, and here you have the output Y, right? For example, if you want to have the same driving capability, if the pull-up path has an equivalent W by L equal to 2, then you would assure that even in a worst case, it should also have equivalent W by L equal to 2. But you know, for the charging case, there happens to be only one case, that is both the transistor, both the PMOSs need to be turned on, then only the charging will happen, right? So having an equivalent W by L means individually they should have W by L equal to 4 and 4, right? So so since the W by Ls are nothing, you can also define them as circuit transconductance, and once there are the conductance in series, the equivalent happens to be in harmonic mean. So equivalent happens to be 1 upon W by L, equivalent of this upper structure is 1 upon 4 plus 1 upon 4. That is 1 upon 2. Hence W by L becomes 2, which is equivalent here. Or in other words, if it is having a resistance equal to 2R, it is also having a 2R, then you can find it out what will be the net resistance, and you will be able to find it estimated, right? Now look at here. So resistance, if you are getting confused, you know that this is having a resistance equal to R. Then if it is 4, then this is having a resistance R by 2. This is also having a resistance R by 2. In series, it happens to be R. Now, in case of pull down, again, this is having a resistance R or equivalent W by L equal to 1. Now, here in worst case, either this transistor should be turn on, or this transistor should be turned on, right? So technically, if you are making sure that the driving capability happens to be the same, even at the worst case, then it should have a W by L equal to 1. It should also have a W by L equal to 1. Yes or no?
Yes, sir.
So what is the net input capacitance which is appearing here? This is
5C.
5C. So what will be the logical effort for this input A? Logical effort for this input A will be
5 by 3.
5C divided by 3C, that is 5 by 3. Agent, this is similar to logical effort for the input B. For the input B also, you have 4 plus 1. Net capacitance here is 5C. Right or not? That
Yes,
is
sir.
5 by 3. Yes or no?
Yes, sir.
So usually the circuits where, if you are implementing a circuits using NAND, NOR, usually you will find it out the symmetrical or similar logical effort for each inputs. But let's say I am implementing a circuit like, let's say A into B plus C whole bar. If I am implementing this circuit, then check. Let us suppose A into B plus C means, let's say this is the A, B plus C means this is B, C, right? This is the NMOS part. What happens to PMOS part? Anyone? I do have the VDD here. A will be in parallel with
B into C.
A will be parallel with
Series of B and C.
C in
Series. B and C series.
series. Now tell me, first you need to size is this symmetrically, as if you are comparing with respect to the standard inverter, which happens to be this one, right? You need to size it with this one. So now for discharging case, the worst case happens, either this path should be on or this path should be on. Yes or no? And the NMOS, the standard inverter, has this W by L. Look at here. This is 1, this is 2, right or not? And here you have a capacitance 3C. So if it is supposed to have a W by L equal to 1, so can I say, if I put a W by L equal to 2 here, 2 here, 2 here, can I say the W by L equivalent here will be 1? Yes or no?
Yes, sir.
Similarly,
Yes,
W by L equivalent here will be 1. Yes or no? It will be, right? Now look at here, the PMOS part. PMOS part, the W by L is supposed to be 2. Equivalent should be 2 in the worst case. Worst case happens, either this path should be on or this path should be on. So they are supposed to have 2 value, and these B and C is supposed to have 4, 4. Yes or no?
Yes, sir.
So now, are you getting different GA? What is the GA? GA is net capacitance appearing at input A is 4C. Yes or no? 4C divided by 3C happens to be 4 by 3. But what is GB? GB is
6 by 3.
see 4C
by
because of this one, and the B input is here, right? So this is how much capacitance?
6C.
6C. 6C divided by 3C. So that is 2. Are you getting? So logical effort, whenever I am defining, most of the time I will be defining with respect to individual inputs. But when you talk about an AND, NOR, these kind of symmetrical implementations, you are going to get the same logical effort. But when you are talking about these implementation of these gates, a logic family, and you are defining, you are treating A dot B plus C whole bar supposed to be a gate, then you can find it out logical effort per input in that way. Anyway, what I feel is that so far you are comfortable with how to find out G, right? So what are the things you have seen so far? One, logical effort depends upon the topology, yes or no? For example, if it is an AND gate, it is different. If it is a NOR gate, it is different, yes or no?
Yes, sir.
Second, it depends upon the fan-in. Fan-in means number of input. If it is a 2-input NAND gate, 3-input NAND gate, 4-input NOR gate, 5-input NOR gate, it is going to be different. Yes or no?
Yes.
The third one, it also a bit depends. A bit means less. It is also a bit dependent on technology, because every time whenever you are making a standard inverter, you are considering what? Mu raised to mu p. Yes or no? A bit dependency of the logical effort happens to be in technology, which is a bit less. But most of the time, if you really see, if you're talking about a topology, you can directly compare. For example, we worked out one problem yesterday. In case of you have a choice that you want to implement a circuit using universal gate, NAND or NOR, that is the CMOS implementation, then you are going for NAND gate. Why? Because its logical effort was less. It was close to the standard inverter compared to NOR. Yes or no?
Yes, sir.
Right? So logical effort, it basically tells about the topology. And if you are going with the fan-in, if you increase number of inputs, what will happen to G? If fan-in is increased, G also gets increased. Right or not?
Yes.
If number of inputs you are increasing, irrespective of the topology, if I can clearly say a 2-input NAND gate will have smaller logical effort compared to 3-input NAND gate. Yes or no? Because you know that if higher the number of inputs, higher will be the capacitances at the input end. Per input capacitance will increase at the input side. Yes or no?
Yes, sir.
So it's very simple to understand. It is dependent upon the topology. It also depends upon the fan-in. It also depends upon the technology, right? Now, another factor which we are going to discuss now is the electrical effort. Okay. So let me start with the electrical effort today, and yeah. So first, you can read down again the things. The logical effort of the logic function mainly depends upon the circuit topology, whether you are implementing it with the NOR, NAND. It also depends upon the fan-in and slightly on the electrical property of the fabrication process used to build it. As I said, mu and raised to mu p will decide the size of the standard inverter, and that will basically, based upon that, you will be telling about the logical effort. Okay, and you can also combine different. I will be telling you this particular term, how to combine the logical effort of individual states in order to find out the logical effort of a chain. But come to this particular parameter, that is the electrical effort H. Now, electrical effort H is important. It describes how the electrical environment of the logic gates affects its performance and how the size of the transistor in the gate determines its load driving capability. So what does it mean? Electrical effort, the simplest formula is basically for electrical effort is, if this is the load capacitance CL and this happens to be input capacitance Cin, then electrical effort is H is CL divided by Cin. So tell me, if you have a back-to-back inverters, let's say one more, I'm putting it here, right? This is the C in. This is the CL, right? Let's say this node has a capacitance Cx, this node has a capacitance Cy, this node has a capacitance Cl. And I want to find out the electrical effort of this complete path, that is the capital H. Small h, I'm defining electrical effort of a stage. And let's say capital H, I'm defining an electrical effort of this complete path. Can you tell me what it will be? It will be nothing but multiplication of individual electrical effort, H1, H2 into H3. What is the H1? Cx divided by Cin. What is H2? Cy is the load capacitance, Cx is the input capacitance. Cy divided by Cx. What is the H3? Cl divided by Cy. That is nothing but Cl divided by Cin. Are you getting my point?
Yes, sir.
So electrical effort, whenever someone asks you, basically it totally determines the load condition. What are it basically based upon the load conditions? It is going to be higher. If the load capacitance is higher, electrical effort is going to be higher. So it tells you. I told you delay is GH plus P. It is very evident. Can you see? Delay GH plus P. Agent, if my load is higher, my delay is going to be more or less. If the load capacitance is higher, is it going to be more or less?
More.
Release
The more.
So the parameter which basically discuss about this load problem, the load and the W by L sizing of a particular transistor is H. It has nothing to do with the G, because G is telling about the topology. Either you are supposed to implement your circuit using NOR, NAND, or what you can do, like what is the logical effort. It talks about the topology, but S talks about the load condition. It talks about what's the WL of your transistor in order to drive that particular load, right? So H is basically a parameter which defines the electrical environment of the logic gates, which affects its performance, right? And the way you compute it is very simple. You just find out capacitance divided by input capacitance. If there is a chain, a big chain, again it is very easy. Again, you should go at the at the last stage capacitance divided by the input stage capacitance. That will give you the electrical effort of entire path. We will be discussing with more examples, and soon it will be clear to you. Now, that day one student asked me, what do you mean by the parasitic delay? So see, parasitic delay here definition is the parasitic delay of a gate is the delay of the gate when it is driving zero load. It can be estimated by the RC delay model. For example, where is the whiteboard? Yeah. A standard look. Let me find out what is the parasitic delay of this standard inverter. What is the parasitic delay P of this standard inverter, right? So what I am doing, by definition, parasitic delay is the delay when it is driving to none. It is not driving any other load. Means it is not connected. Means if it is not driving any load, what will be the parasitic delay? What will be the capacitance here? If it is not driving any load, this capacitance will be diffusion. Only due to the capacitance, diffusion capacitance appearing here. Yes or no?
Yes, sir.
I told you,
basically 3C.
in the RC delay model, there are the three capacitances, right or not? One capacitance is here, another capacitance happens to be here, another capacitance happens to be here in case of NMOS, right? So if someone asks you what is supposed to be the capacitance here, it's very easy. 1C because of this transistor, 2C because of this one transistor, it happens to be 3C. Now, for either case, be it charging case, your resistances are, for be it discharging case, your resistances are. So what is going to be a parasitic delay? 3RC. Yes or no? When it is not driving any load. Yes or no?
Yes, sir.
yes,
Always do remember, whenever I write GH plus P, always do remember, let's say I have this thing, one capacitor here, one inverter here, and one inverter is driving for another inverter, one inverter here, another inverter here, another inverter here. Tell me what will be the if I say the capacitance of this particular inverter. This inverter is identical to this inverter, this inverter, this inverter. Means all the inverters are identical. And if the input capacitance here happens to be C, what will be the capacitance here? Can you tell me?
So 4C.
4C. Now don't get confused, sir, why we are not including output capacitance of this thing. Output capacitance of this one we are not including because it is already been taken care of by parasitic delay P. Are you getting my point? We are only considering it their input capacitance, which is C here, which is C here, which is C here. We are not talking about its output capacitance because this output capacitance is already been taken care by the parasitic delay term in the equation. Are you getting me? Yes or no?
Yes, sir.
In better way, in logical effort theory, we don't tell the P is supposed to be 3RC. We always normalize this capacitance also by its input capacitance, input value of the delay. If this is the 3C, and if you normalize, let's say if this net capacitance happens to be here 3C, and if you normalize it with the input capacitance, then what is going to be the value? What is the input capacitance here? 3C, yes or no? So roughly it is 1. Yes or no? What I'm doing,
Sir, can you repeat this?
I'm saying instead of writing this as a delay 3RC, because finally see, if you know the unit is GH plus P into tau, correct or not? Tau, it gives you the unit of the second. This is unitless, this is unitless, this is supposed to be unitless, yes or no?
Yes, sir.
It is supposed to be unitless. If you put P equal to 3RC, what is going to be unit? Unit is going to be the second and multiply by the second. It is going to be, everything will be messed up, right? So in order to make it consistent with the linear delay model, this parasitic delay of this particular inverter is basically is normalized against the capacitance of against the input capacitance. If I say output capacitance happens to be here 3C, this is divided by the input capacitance here. This is again 3C. This is my parasitic delay of an inverter, P inverter, which is closely equal to 1. Yes or no? Unless you are making this diffusion capacitance smaller. Can you make this diffusion capacitance less than gate capacitance? Can you do it? Can you do it or not?
Wait.
No.
Junction sharing.
I'm saying if I need to define a parasitic delay of an inverter, I told you the parasitic delay of any logic circuit is defined by it is the net. What is the impact of the intrinsic parasitic on the delay, right? So we are not taking any load here. We are saying whatever the internal capacitance is here, internal capacitance happens to be 3C here. And I said, in order to fit this particular parameter into the equation, that is GH plus P times tau, you need to make this P unitless, and that is why you are basically normalizing against with input capacitance. So it happens to be 3C divided by 3C, which is 1. But you will find it out, there are certain technology where parasitic delay, that is P inverter, is going to be less than 1. For example, can you tell me, any one of you have heard of silicon on insulator, SOI?
Yes, sir.
In silicon on insulator, you will find it out, this diffusion capacitances which happens to be here, they are less compared to input gate capacitance. If numerator is going to be less compared to the gate capacitances, the P inverter you can get almost like 0.6 to 0.8. Usually in SOI. You're getting my point?
Yes, sir.
Now, what I am trying to say is in GH plus P, G happens to be logical effort, very easy to calculate. H happens to be electrical effort, very easy to calculate. And P is the parasitic delay. And every time you define the parasitic delay, you define with respect to P inverter delay. P inverter happens to be parasitic delay of inverter. If in exams or somewhere it is not given what is the P inverter, you may choose it to be 1. If you are working with the SOI technology, you will find it out. This internal, this parasitic delay happens to be less than unity. Okay, but if it is not given, then you are supposed to tell it 1. For example, I ask you, please, all of you, please just check and tell me, if I have a 2 input NAND gate, 2 input NAND, the first thing I will be making 2 input NAND. So tell me, in order to make it equivalent WL or equal to 1, can I make it 2 2? The standard inverter, the lower path I want to make it 1, and upper path I want to make 2. So this is 2, worst case. Yes or no? So far so good?
Yes, sir.
So can you compare what is the parasitic delay for this NAND gate? Now tell me, for this NAND gate, what is the net capacitance happening here?
460.
60.
2C because of this one, 2C because of this one, 2C because of this one, 6C. 6C. Yes or no?
Yes, sir.
So agent, this is 2 times more than the parasitic delay of this particular inverter, which is having 3 RC delay. This is having 6 RC delay. Agent, this is 2 times more than this particular one.
Yes.
Yes or no? The delay here was 3 RC and delay here is 6 RC. Yes or no? So can I say 2 input NAND gate has a parasitic delay equal to 2 times P inverter? Can I say? I need your response.
Yes, sir.
Yes, sir.
Or in other words, I can generalize this statement as saying an input NAND or an input NOR has a parasitic delay equal to n times of P inverter. Is it okay? Want to verify? Then you can also verify for the 3 input NAND gate. For 3 input NAND gate, what is the capacitance here?
8.
9C. Agent, have you forgotten? In RC delay model, we did it. What was the load capacitance you are getting there?
9C.
9C.
9C. 9C divided by 3C is 3. So 3 times of P inverter. So similarly, you can work it out for 4 input NAND gate. Similarly, you can work it out for the NOR gate. You will identify that parasitic delay is going to be n times of P inverter delay. Understood, all of you?
Yes, sir.
Yes, sir.
So someone asked that particular day, that is yesterday, that what do you mean the parasitic delay? Parasitic delay is the delay which is intrinsic delay when the gate is not driving any other load. Means if the gate is not driving any other load, means internal capacitances are contributing into the delay. You're getting my point? Also, I told you parasitic delay of inverter is the ratio of the diffusion capacitance to gate capacitance. As we said, diffusion capacitance happens to be 3C, gate capacitance happens to be 3C. So you are getting almost figure equal to 1. But again, as I said, if you are going for the SOI technology, you will find it out the diffusion capacitances are less. Since the diffusion capacitances are less, because SOI is the silicon on insulator, so it's ultra thin. You have silicon over an insulator, so you know that this source and drain region, the diffusion area, you are suddenly getting this SOIs, that is the insulator. You're not getting this diffusion. Diffusion is not extending into the insulator, so it happens to be less, right? So these capacitances like diffusion capacitance is less in SOI technology that you can check. It's very simple if you go with the device of SOI, right? But in general thumb rule says that if it is an input NAND gate or an input NOR gate, then the parasitic delay will be n times of P inverter. You're getting my point? Yes or no?
Yes, sir.
And last but not the least, that parasitic delay has nothing to has no role of the width. Means you know that if you increase the width, someone can say R will reduce. R will reduce, but other day one student told me if width is increased, the C will increase. So effectively, RC product happens to be constant. So increasing transistor size reduces resistances but increases capacitances correspondingly. So parasitic delay on first order, a first order understanding is independent of gate size. That is again one important point you need to take care. So far we have talked about the delay. Delay happens to be G into H plus P. That is logical effort multiplied by the electrical effort, which is also known as effort, net effort, right? Effort delay, F, plus P, and the unit happens to be tau, and we are comfortable with each and every term, right? So let us, so if someone wants to really see the derivation of this one, how do we reach this delay equal to GS plus P? A simple transistor as a switch model has been discussed by the article which has been shared to you. You can simply go through it, but we will be directly using this particular one. Delay is nothing but GS plus P times tau. Let me go with the one terminology which we basically coin every time when we talk about a digital circuit, that is FO4 delay. FO4 stands for example, estimate the delay of a fan out of 4 inverter means one inverter is driving identical, how many inverters?
4.
4 inverters. And this is a very standard term. Every time they will ask you, if they don't give you the value of tau, if they don't give you the value of tau, they will ask you what is the delay of this particular chain of the circuit compared to with respect to FO4 delay. Means you should be first knowing what is the FO4 delay in your technology. For example, right now, can you tell me what is the delay here? This delay in FO, like one inverter is driving 4 inverters. So can you tell me from here? Let's say this is the input to output here. What is going to be the delay? Delay is G into H plus P. What is the G for inverter? G
So
of
one.
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 1. What is the H here?
4.
If this capacitance happens to be C, then capacitance here happens to be how much?
4.
4C. So H is 4C divided by C plus what is the parasitic delay of inverter? P inverter is supposed to be 1.
1.
So FO4 delay is how much?
5.
5. The unit is tau. Understood? So if I say if a circuit gives me 30 tau delay, if any arbitrary circuit gives me 30 tau delay, then what will be this delay in terms of FO4 delay? Can I say this delay is 6 times of FO4 delay? Can I say?
Yes, sir.
Yes, sir.
FO4 delay is 5 tau, but someone can ask you what is the FO4 delay. If a circuit is giving you 30 tau, you can say this is 6 times of FO4. Clear or not? So far. From BTech students, Shreyank, things are clear so far?
Yes, sir.
Now, it is not that method of logical efforts are simply used to calculate the delay, but they are the effective means to optimize a chain, to optimize basically a critical path in a circuit. I told you if you look at the processor, then there are, let's say if there are 100% path, then only 20% of the path within the processor happens to be the critical path. Means these are the paths where you need to pay your attention in order to optimize this path for the high speed, right? Only 20% path. So method of logical effort serves a good tool if you are basically, if you want to optimize a particular critical path. Okay, then how it is, before we go ahead and I explain you how to optimize a particular path, let me again build up with couple of more example, couple of a bit more theory. That is, so far we have talked about the logical effort of a logic gate, but now we will be talking about the logical effort of a path, logical effort, similarly electrical effort of a path. We will also introduce one more term, that is the branching effort, and then we will start. So here, if you have, let's say, if you have a circuit like this, if your critical path happens to be like this, one inverter, then 2 input NAND, then another inverter, and the critical path input is A. From A to output Y happens to be your critical path. Now, what will be the path logical effort? If the G1 is the logical effort here, G2 is the logical effort here, G3 is the logical effort here, the path logical effort is G1 into G2 into G3. So can you tell me in this example what is that? G1 is 1, G2, if the mu1 raised to mu p is 2 raised to 1, what is the G2? What is the G2? 2 input 9.
So 5/3.
Do it again. Is it 5/3 or something else?
4/3.
4/3.
4/3.
Right? It is the 4/3. So you are getting my point. If someone asks you what is the path logical effort, you have simply you just need to multiply G1, G2, G3. Understood? Understood? Yes or no?
Yes, sir.
Similarly, if someone says what is the path electrical effort, that is capital H. I told you even you multiply H1, H2, S3, H1, S2, S3, even you multiply, it doesn't mean, because finally the numerator and denominator will cancel each other and you will end up getting C out divided by C in. Yes or no?
Yes, sir.
Yes or no? Similarly, there is one more term which is path effort, because you know that small effort F was defined as G into H. The path effort F is nothing but multiplication of all these, like G1 in H1 into G2 S2 into G3 S3, and this is known as capital F. Now tell me all of you, that how likely you will get this kind of chain. Usually the chain is not like that. You also have some branching. For example, though this happens to be critical path, but at this particular node there happens to be one more branch. That output, that this gate is driving not only a single inverter, but it is also driving another inverter, though this may not be in the part of the critical path. Critical path happens to be like this. I can use a different color. The critical path happens to be this one only, but there is a branch. Yes or no? Can you see a branch? Similarly, let's say at this node there is another NAND gate. There is another branch, right? But the critical path happens to be this one. Isn't these branches are going to slow down your response?
Yes, sir.
They are going to slow down because some of the current will be given to these gates, right? But so far, I don't know how to respond to that. But so far, we have not captured these branches anywhere, right? For example, either I need to see what is the capacitance offered by here, and I need to put the capacitance here, and then I need to tell what is the H. Either I need to modify the H, or I can define another parameter which is the B. Okay. So branching effort is defined as very simple: capacitance in on path plus capacitance of off path divided by capacitance in on path. For example, if an inverter is driving a NAND gate, the same way you just look at here, then it is driving in another NAND gate and another inverter. Then you have one more inverter here, you have one more inverter here, and these inverters are identical. Okay, but your critical path happens to be like this. The critical path happens to be from input to output. This is the critical path, right? Then you know that at this node there is no branch, but here there are the branch, right? So what is the net capacitance in on path? Let's say this capacitance happens to be C. Then C plus what is the net capacitance of on path if this is identical with this one and this is identical with this one? Can I say the off path capacitance means capacitance in this path plus capacitance in this path? This is 2C divided by what is the on path capacitance, that is C. That is nothing but 3. You are getting my point?
Yes, sir.
Capacitance in on path plus capacitance in off path divided by C on path. If you do it, you can find out the branch effort. What is the branch effort here? Capacitance in on path is C, or there is no off path, the capacitance in off path is 0 divided by C on path. So C by C happens to be unity. So B1 here is 1. At this node, you can see the B2 is 3. So net branching effort is B1 into B2 into B3 into so far. So this is 3. Understood? Understood so far? So if someone asks you what is the effort of a path, you can say F is not simply G into H, but it is also G into H into B, or you say G B into H. This is your path effort. If someone asks you what is the path effort of a chain, this capital F happens to be G into B into H. Okay? This is the one. We will be doing a couple of exercises, but before that you should be knowing why we are doing all these things, right? That must be a question. Okay. Now, let's summarize each and every point. If you have a chain, let's say you have a chain, arbitrary chain. Again, I'm going with the same example which I just coined for now. And this is the critical path. I mean, this is the C out. This is the C in. Then tell me, what will be the delay in this path? Anyone can tell me the delay? If I say the delay offered by this inverter is D1, delay offered by this one is D2, delay offered by this one is D3. Can I say the net delay is nothing but the summation of all the delay? Can I say delay is nothing but summation of all this delay? Yes or no?
Yes.
What is the delay of D1? Can you tell me? G1 H1 plus whatever the parasitic delay. This is inverter, so it is P inverter, or you can say P1 for simplicity here. What is the D2? G2 S2 plus P2. What is the D3? G3 S3 plus P3. In other words, you can say sigma of Fi means sigma of Gi Hi from I equal to 1 to 3 plus sigma of Pi. I equal to 1 to 3. That is, this part you can say capital P and this part you can say D. So this is how you can calculate the delay. But still our objectives are not here to simply compute the delay. Our objectives were, what were our objective? To optimize the delay, yes or no? So far we have not done the optimization, we have just computed the delay. You are getting my point? Yes or no? So far. Any confusions till that? Are you seeing? Anvesh,
No, sir.
things are clear so far?
Yes, sir.
Okay. Now coming to the optimization. Now first optimization problem which we are starting now is optimizing the delay for a given path. We are not going to change like how many number of stages are there within a path. We are going to find out what will be the optimum sizing in order to give you the least amount of the delay. What will be the optimal transistor sizing in order to give you the least amount of a delay, right? So let me tell you one example before we go ahead. Let's say one NAND gate, 2 input NAND gate is driving. I'm giving you a simplest example, a NOR gate, right? And this A to Y, this I can say this is my C out. And I also know what is my input capacitance, that is C in. So what will be my path electrical effort, anyone? This is C out divided by C in. Yes or no? Path electrical effort.
Yes, sir.
Will it be C out by C in?
Yes, sir.
Also, I told you this H is nothing but also if you can mark what is the CX here, you can say this is nothing but H1 into S2, right or not? H1 is the electrical effort of this one, S2 is the individual electrical effort of this one. If you multiply, you will get C out divided by C1. Yes or no?
Yes.
So similarly, the logical effort here happens to be how much? G1 is the logical effort here. Let's say G2 is the logical effort here. Though you may compute the G1 and G2, but I am just putting it as the formal expression because I want to first make a theory. I am basically trying to establish a theory to optimize a given path. So I'm not going with the numbers right now. Okay. So what will be the delay? Can I say delay will be delay of one stage plus delay of another stage? If I say this stage gives you D1 delay and this stage gives you D2 delay, can I say delay is nothing but D1 plus D2? Yes or no?
Yes.
Can I say the delay of one is G1 H1 plus P1 and delay of 2 is G2 S2 plus P2? Can I say?
Yes, sir.
Can I rewrite this expression as, please look now, G1 H1 plus G2 capital H divided by H1 plus sigma of parasitic delay, where sigma P is P1 plus P2. Can I say S2 is nothing but H divided by H1 because I know H is constant, C out by C in. Any problem so far?
No, sir.
Is it clear? So if you
Yes,
want
sir.
to minimize this D, then can I do this particular thing? Del D by del H1, it needs to be equal to 0. Then you will get what should be the value of H1, or you should get a relation which will give you the least value of the delay. Yes or no? This is what you do in order to find out maxima and minima.
Yes, sir.
So if I do so, and I keep this del D by del H1 equal to 0, then what I will get? G1 plus, sorry, minus G2 by into H divided by H1 square plus 0, because P is also not dependent upon H. Yes or no?
Yes, sir.
So what I get? G1 into H1 square is G2 into H. And you know that this G2 into H is nothing but H1 S2. Yes or no?
Yes, sir.
H was H1 S2. So can I say this happens to be this one, that G1 H1 should be equal to G2 S2. So what you are getting? Can you see it? What we are getting now, that you are having this circuit. You are having this circuit. And if you want to assure that this circuit gives you the least delay, then you need to make effort delay of this one, which is G1 H1. This must be equal to effort delay of this one. This should be G2 S2. Are you getting my point? Means this guy should give you this, put the same effort as this guy should give this, provide the same effort. Means effort delay of this one, G1 H1, has to be equal to G2 S2. Are you getting my point? All of you?
Yes, sir.
If it is so, if the G1 H1 and G2 S2 are same, in that case the D will be minimum. The same thing I want to generalize if there are 3 stages. If there are 3 stages, or maybe if the 4 stages. Let's say this stage has a G1 H1, this stage has a G2 S2, this stage has a G3 S3, this stage has G4 H4. Then what should be the expression now? What should be the condition for the delay? When G1 H1 is equal to G2 S2 is equal to G3 S3 is equal to G4 H4, then you will get least delay. Are you getting my point? That each stages provides equal effort. Means effort is small f equal to G into H. G1 H1 is equal to G2 into S2 equal to G3 S2 equal to G4 H4. Means every stages are bearing the same amount of effort. You will get the least value of the delay. Understood?
Yes, sir.
Understood? Now, if all of you just look, G1 H1, G2 S2, G3 S3, G4 H4 are equal. Do you know how we were defining capital F? Capital F was multiplication of all GH. If G1 H1 is multiplied by G2 S2 is multiplied by up to Gn, n means n number of stages, Hn, then you know that all these things are supposed to be equal. So can I say this optimal stage effort F cap or GH cap is nothing but F to the power 1 by n? If there are n number of stages, yes or no? Because G1 H1 is, let's say, is equal to G into H, then it becomes GH whole square, then GH to the power n. So isn't optimal GH is nothing but F to the power 1 by n?
Yes, sir.
Right or not? The second thing, if G1 H1 G2 S2 are equal, and let's say there are n number of stages up to n, can I say the delay is nothing but n into G into H optimal plus summation of all the parasitic delay from I equal to 1 to n. On another word, I can say delay is n into F to the power 1 by n plus delay caused by all the parasitic delay. This is my going to be the D minimum. Yes or no? Yes or no?
Yes, sir.
Very simple, na? If you are having G1 H1 G2 S2 here 2 times, so this is 2 times of G1 H1. But you know, since G1 H1 G2 S2 all are same, which is equal to GH cap, I can say n times of GH cap. On other word, GH cap is nothing but F to the power 1 by n. So I can have a relation that delay will be minimum if all the GH are the same throughout the chain. Means I need to ensure that G1 H1 should be equal to G2 S2, should be equal to G3 S3. This is, as a designer, I need to ensure. If I have ensured this particular thing, my delay happens to be nothing but n times of F to the power 1 by n plus summation of all the parasitic delay throughout the path. Understood? Yes or no?
Yes, sir.
So far, so good. I think you will be doing it better if I will be telling you how to size your transistor later on. But first, me give you one example so that you can apply. If you apply, then you become more confident. Yes or no?
Yes, sir.
Yes or no? If you can apply this particular one in this particular problem, then you will be more confident. What is the general understanding we have find it out? Let's say first I will discuss this question. Estimate the minimum delay of the path from A to B. A to B. So let's say this is my critical path. First you find out, choose the transistor sizes to achieve this delay. That is okay. But first we need to find out what will be the minimum delay from the path A to B. And then how to achieve this particular delay. How to make sure that this condition happens. Okay, both are the things here. Now, you know that this will have G1 and H1 as G1 will be the logical effort, H1 will be the electrical one. This will have G2S2, this will have G3S3, right? So if I say mu1 raised to mu p happens to be 2 raised to 1, then first tell me what is the G1? What is the logical effort of 2 input NAND? Please tell me.
4 by 3.
What is the logical effort of 5 input NAND? Sorry, 3 input NAND.
3.
G NAND 2 you are saying is 4 by 3. G NAND 3 is
3:2.
I need one answer from the class now. What is the logical effort of this NAND gate? 3 input NAND gate.
5 by 3.
Very simple. You just put it here. Na? I can hear the multiple answers. I'm not getting why I'm getting the multiple answers. Yes sir.
5 by 3.
हाँ क्लास में बस 10 मिनट में फ्री हो रहा है. Yeah.
5 by 3.
5 by 3. But still,
Yes, sir.
I can see only few of you are answering. What about others? So you can see, in order to make it like 1, you need to keep it 3, 3, 3. And these transistors are supposed to be how much? 2, 2, 2. So 5C here, 3C here. So this is 5 by 3. What is the logical effort of 2-input NOR gate?
5/3.
5/3.
So what is the capital G? Multiplication of all. How much?
100 by 9.
100 by
20.
27.
100 by 27.
27.
What is the H? H is, this is the value of the input capacitance which is given here. This is the value of the output capacitance which is given here. H is 45 by 8. This is the input capacitance. This is how we will be giving you in the exam as well. Okay. And this is the capacitance here, the 45 by 8. Is there any branching effort here at this node? Yes, there are the branches. The current is getting divided into 3 branches. Yes or no? If the capacitance happens to be here Cx, Cx is the capacitance because of this one, Cx will be the capacitance because of this one, Cx will be the capacitance because of this one. What will be the net capacitance here? You will get the 3C. In other words, the branching effort will be C on path capacitance is Cx plus off path capacitance is Cx plus Cx, that is 2Cx divided by on path capacitance Cx. So branching effort here happens to be B1 happens to be 3, right? Similarly, branching effort happens to be here how much? 2. Here are 2. Yes or no?
Yes, sir.
So what is the net branching effort? Capital B happens to be 6. 3 into 2, that is 6. So can you find out what is the F? Path effort. Path effort is G into B into H. How much? 100 by 27 into 45 by 8 into 6. How much you are getting?
125.
125. Right? This is 125 we are getting, all of you please make a note of that. If this is 125, then tell me how many number of stages are there in this particular circuit? 1 stage, 2 stage and 3 stages. There are 3 stages, yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So this circuit which has F equal to 125, number of stages N equal to 3, in order to get the minimum delay, the condition says G1 H1 should be equal to G2 S2, should be equal to G3 S3, should be equal to optimal value, that is GH cap. And this GH cap is F to the power
1 by n.
1 by 3. That is how much? 5.
5.
You are getting my point, all of you?
Yes, sir.
Yes.
Now listen, now see. What is the delay? What is going to be delay now? Delay is going to be how many number of stages? 1, 2, 3. N is 3. 3 into 5 plus parasitic delay of this 2-input NAND gate. How much is the parasitic delay of this 2-input NAND gate? 2 times of P inverter. P inverter delay is 1. 2. What is the parasitic delay of 3-input NAND gate? 3. What is the parasitic delay of 2-input NOR gate?
2.
2. That is how much?
7.
15 plus 7. How much?
22.
22.
Tau. This is going to be our minimum delay. But in order to achieve this, you need to ensure this condition. Yes or no? You need to ensure that G1 H1 should be equal to G2 S2 should be equal to G3 S3 should be equal to 5. Yes or no?
Yes, sir.
In order to get this least amount of delay, you need to ensure this G1 H1 of this stage should be 5, G2 S2 of this stage should be 5, and G3 S3 of this stage should be 5. Let me start from this node. Then look, G3 into S3 should be equal to 5. What is the S3? Can you tell me? What is the G3 of this one? G3 of this 2-input NOR is how much?
5 by
5 by 3.
5 by
5
3.
by 3 into X3. X3 is C out divided by C in. C out is 45 divided by C in. C in is CY. Let's say this capacitance happens to be CY. Okay, that is supposed to be 5. So how much you are getting? The CY is supposed to be how much? 15. Correct or not?
Yes, sir.
Am I able to find out the capacitance at this node? Yes or no?
Yes,
I'm
sir.
able to find out the capacitance here. What about here? Can I say G2S2 is supposed to be 5? G2S2 is supposed to be 5. Now look, what is the G2? 3 input NAND gate. What is the G2 for the 3 input NAND gate? Logical effort.
5/3.
What is the H2? Please tell me, what is the H2?
15 by CX.
That is the mistake. 15 is the capacitance at this node. 15 will be the capacitance here. Net will be
30.
30. Yes. 30 divided by CX is 5. Yes or no? Because 15 was the capacitance of here. Then 15 will be the capacitance here. Effective output capacitance happens to be 15 plus 15. That is 30. Yes or no?
Yes, sir.
So this is 10. This gets cancelled. So what is the CX?
10.
10. Now I want to see whether my answer is correct or not. Have I committed any mistake or not? I need to again cross check. What is the G1 H1? G1 H1 is supposed to be 5. Yes or no?
Yes, sir.
So what is the G1?
4/3.
4/3. What is the H1?
30 by.
H1 is 30 by.
30.
Let's say
8.
some capacitance EA.
Eight.
That is supposed to be 5. Now you look. 10. This happens to be 2. Are you getting CA equal to 8?
Yes, sir.
Have you verified that this capacitance was already 8? Are you getting, is their computation is correct? Yes, your computation is correct. Because you started from this end, you came to this end, you came to this end, you came to this end, and you ended up getting the same value. Yes or no?
Yes, sir.
Yes.
In method of logical effort, it's very easy to verify your computation. You're getting my point? You find it out, this value happens to be how much? Kitni thi bhai, phir se batao. CX was 10, I do remember. This was how much? 15.
Yes, sir.
And this was 8. So you have find it out intermediate capacitances 15, 10, and other thing. If you know the capacitances, can you also comment on the size? This is my question. If you know input capacitances, because input capacitance is nothing but, for a gate is nothing but W into L into COX. Yes or no? Yes or no?
Yes,
In the
sir.
SPICE, COX is given. In the SPICE library, COX is given. Length, you choose the minimum length. L into COX is known to you. And this happens to be the capacitance. So if I know the capacitance here, am I also able to see width? For example, I will tell you, don't be worried. For example, let me take this case. You have this NOR gate. So can you make a NOR gate first? NOR gate happens to be PMOS in series or parallel? NMOS will be in parallel.
Parallel.
And the PMOSes will be in
Series.
series. Right? Right. Now, tell me, what should be the sizes here? At least the ratios of the sizes. I know that if you want to divide it with the method of logical effort, you will be putting the sizes accordingly. Right? So I can say, if this is supposed to be my, if the lower one is supposed to be make W, I will put its W size here, W size here. If this is W, this is W. What should be the size I should be putting here? This should be 4W. Right or not? Right or not? So at one input, how much capacitance I'm getting? I'm getting 5W into COX into L. Yes or no? At one capacitance, this capacitance CG is 5 into net capacitance. Capacitance happens to be W into L into COX. Yes or no? Yes or no?
Yes, sir.
Yes, sir.
Right? So this is at one end, and this is supposed to be how much? 15. This is supposed to be 15. So can I say the width of, if the COX into L is unity, let's say for simplicity, this is unity, though it will be unity, some femtofarad, some units will be there. Can I say width is supposed to be, the lower transistor should have a width equal to 3 3, and upper side transistor should have a width equal to 12. Can I say?
Yes, sir.
Can I say this particular one? Look, and if you size your transistor, then PMOS is 12 times, NMOS is 3 times. Then similarly, you know that this value here was how much? 10. 10 here, 10 here, right or not? Right or not? So this PMOS is sharing 12 unit of capacitance here. It is sharing 3 unit of the capacitances. Similarly here, 10 unit of capacitance means 4 will be because of the PMOS and 6 will be because of the NMOS. You're getting my point, all of you? Not yet, not totally confident. Is there any doubt? Rakesh? Macha Rakesh?
Yes, sir.
Any doubt?
Sir, please tell previous one which you were telling.
I think I'm saying, let's say I say W into L into COX supposed to be 1 unit, right? I'm saying net capacitance here is supposed to be how much? 15. It came as 15, right or not? 15 unit capacitance. 45 unit here, right or not? Is this could be 45 femtofarad or something? It will not be 45 farad here. It will be femtofarad unit. 45 unit here, and let's say this capacitance here came as 15 unit. Now I told you how to divide this capacitance, because ultimately we need to size the transistor W by L, right? Ultimately we need to find out W by L, yes or no?
Yes, sir.
Yes, sir.
So for this PMOS, first you basically put this transistor, just make the schematic of this particular circuit. If you make the schematic, you know that there are 2 PMOSes which happens to be in series, and there are 2 NMOSes which happens to be in parallel. You know that if this is supposed to be of the net equivalent supposed to be 1, and here it is supposed to be 2. So you need to put 4 here, 4 here, 1 here, 1 here, right? Let us suppose I'm multiplying, because sizes doesn't mean you need to maintain this ratio. You need to maintain this ratio. If I say this is X, this should be 4X, this should be 4X. Now look at per input. Per input, what is the capacitance appearing here? W into L into COX. What is the width now? 5X into L into COX. That will be the capacitance, yes or no? Jaldi batao.
Yes,
Yes, sir.
5X into L into COX. Let us suppose
15.
this L into COX happens to be unit per micrometer or something. Whatever the unit, femtofarad per micrometer, whatever L into COX unit comes, that is given by this 15 units here, right? So unit and units are cancelling. So what you will get? You will get X equal to how much? 3 micrometer. If X is 3 micrometer, what you will get? Can I say this NMOS should have a size equal to 3 micrometer, 3 micrometer, 12 micrometer. PMOS should be 12 micrometer, 12 micrometer. Can I say yes or no? If you
Yes,
know the
sir.
value of L into COX, can you compute these things or not? Just tell me this thing. If I give you L into COX, can you work out and find out the value of width of PMOS and NMOS? Yes or no?
Yes, sir.
You can because 2 by 1 is a standard size of inverter, but it doesn't mean that you need to keep 2 by 1 only. You can have 2x and x. Still the ratio is maintained as 2. You're getting my point?
Yes, sir.
So now, if I mean, if you know, so what we are doing, just look at here. We started approaching the problem in this way. We first find out the value of f, then we find it out what will be the optimal value of gh, which was nothing but f to the power 1 by n. Then I said, in order to have the least amount of the delay, g1, h1, g2, s2 all should be equal, right? This give you this. You started from last stage, that give you the value of the capacitance here. Then you went with this one, that give you the value of capacitance here. Then you cross verified with this one. As soon as you have the capacitances and you know the value of L into COX, which is given to you, you can also compute what should be the width of your transistor. That is what you need to know as a design engineer. You should be able to size the transistor width, right or not? Yes or no?
Yes, sir.
Anyway, I know that this will take a bit of time to digest. Unless you do it by yourself, you will not get the confidence. So I am leaving you with one problem which you can practicize, and here I have given you the value of L into COX as well. Look at here. The critical path of a logic circuit is shown from node A to node B, right? And node A, the capacitance at node A is given as 4 femtofarad. This input capacitance is given as 4 femtofarad. So can you tell me what is the capital H? H is how much?
25.
25.
Can you also find out what will be the G1 here, what will be the G2 here, what will be the G3 here, what will be G4, what will be the capital G? You can find it out, yes or no?
Yes.
Can you also tell me your branching effort? Branching effort of capital B is 3 into 2, that is 6. So this will give you F equals GBH. So what will be the optimal value of GH? F to the power how much? 1 stage, 2 stage, 3
1
stage,
by 4.
1 by 4. This will give you the optimal value. And once it gives you, can you find out intermediate capacitance CX, CY, CZ? Can you find out CX, CY, CZ?
Yes.
Having find it out CX, CY, CZ, and I also provide you one important thing here. Look, I told you keep L equal to L minimum, 250 nanometer, that is 0.25 micrometer. Keep L equal to 250 nanometer. And COX is given to you. Do you have L into COX? Do you have L into COX? Yes or no?
Yes, sir.
If you have the L into COX, can you find out what should be the width of these transistors, NMOS, PMOS here? What should be the width here? What should be width here? What should be width here? Yes or no?
Yes, sir.
Yes, sir.
But you need the time.
Yes.
So take a snapshot. Take a snapshot, all of you. Take a snapshot. Next class is on Thursday. It is on Thursday or when? I think on Thursday, right?
Yes, sir. Yes, sir.
Take on the snapshot, all of you. The CRs may share in the group if they have taken the snapshots. Are we done?
Yes, sir.
That's good.
सर इसमें L minimum क्यों ले रहे हैं?
I just for simplicity I'm telling L, take L equal to L minimum. If you want to keep it, put it, I told you, if you keep changing the L, it will have a consequences at what consequences I told you. The gate capacitance happens to be W into L into COX, but diffusion capacitances are only they are not proportional to the length.
Yes.
Right? Usually the practice is basically you don't change the length much. In analog applications, you do sometimes change the L, or you go with the higher value of L. Let's say you are working with the 65 nanometer technology, but you may choose L equal to 1 micrometer if you want to reduce early effect, or you want to increase the RO, because RO, you know that output resistance is proportional to 1 upon lambda ID, and lambda is inversely proportional to L. So if you increase the L, lambda is less lambda effect. So sometimes if you want to increase the RO, you do it in analog, but usually in digital you keep the L, you fix the L to be minimum. You only change the width. Usually this is the practice. Okay? You know the current is proportional to W by L. If I keep L fixed, still I can change the width in order to get the required current. Yes or no?
Yes, sir. Got it.
Yeah. So I think even after this lockdown, it was a very long lecture, right?